In our last video, we arrived at the expression for the molecular partition function, right? So we put together the individual terms for each degree of freedom, multiplied those all together, and so we now have our molecular partition function, lowercase q. Right? In this video, we're going to begin to develop ways to get from partition functions to values for actual thermodynamic functions, enthalpies and things like that. First thing we have to do is get away from having a single molecule, right? Because the molecular partition function is, at least in principle, calculated by thinking about what are the energy states available to one molecule, okay? If I have a collection of n molecules, and if we start off with the case that the molecules are distinguishable, then we could write that our partition function for that collection, which becomes uppercase q here, is just q to the n, right? When it says the molecules are distinguishable, that would be the case if, for example, we were talking about molecules that were arranged in a solid crystal, because in that case, each molecule could be given its own set of coordinates, right? Its own lattice point, and that would make it easy to tell them apart. If, on the other hand, we had the molecules in a gas, then there is no real way to label a single molecule, right? Because the positions are going to constantly be changing, and so two molecules could easily trade places with regard to their locations within the container, for example. Right? In that case, we have to introduce this n factorial term down here. What that does is it avoids counting what would essentially be identical configurations, right? Because I could take any pair of molecules and trade them for what states they were in, and I would get what is really the same distribution, right? So I don't want to count that more than once. Right? And so we have those two versions of what happens if we work with a collection of n molecules, where n, particularly if we're talking about the molecules in a gas, is presumably a very large number, right? So that thing is not going to be trivial to calculate because it's got an n as an exponent and an n factorial in it, and both of those are going to generate very large numerical terms in most cases. So the simplest case to take is just a monatomic gas, right? Think helium or neon, something like that, right? Monatomic gas acting like an ideal gas, and so helium would be a great example because it's got the weakest intermolecular forces, so it's the closest to actually being an ideal gas, right? If it's all the atoms are in the ground electronic state, which would be a reasonable conclusion, right? We would not expect at any kind of normal temperature to have a real chance of finding a helium atom that had an electron in anything other than the 1s orbital. So there's only translational motion, right? I just have a single atom. That's a point, so I can't vibrate it. I can't rotate it. All I can do is let it fly around through space, right? So that says the only partition function I need to account for is translation, right? And so I take my my expression that we had before, this one. This piece in here, that thing in the square brackets, that's our translational partition function for a molecule, right? Where m in there is the mass of the molecule and so on. V is the volume of the container, right? So that if I now have n molecules, I have to take that and raise it to the n power, and then I have a 1 over n factorial term there to account for the fact that the molecules are indistinguishable. Right? That gets me this rather awkward looking expression up here. And that one says that I have still got that n factorial term down there. So imagine that I'm talking about, say, a mole of gas or something like that. That's still a thing that's going to be not very amenable to calculations. I could take that and I can use what is known as Stirling's approximation, which says that for large values of n, we can make this substitution. Right? And that gives me an expression that says I could rewrite this in a slightly simpler form like this one down here, right? So that's an equation that at least in principle would let us work with this thing and get this partition function, okay? Trying to evaluate that and get a number for it is in fact going to prove very daunting likely because the quantities in there are going to be so large, right? Again, if I take n and I put in Avogadro's number, even though I've gotten rid of the factorial, I've still got you know, like on the bottom, I've got n to the nth power, right? And if that n is 10 to the 20th power, then that's something that I'm not really going to be readily able to evaluate. But we can still do a lot of things with the expression, right? Because many of our relationships that are going to get us to the thermodynamic quantities are going to depend on things like the derivative of this partition function with respect to temperature and other things along those lines, right? And those we could still potentially find and get useful expressions from. Take a moment and talk a little bit about something known as the canonical ensemble. Okay, in statistical mechanics, if you study the topic in more detail, there are a variety of different ensembles. There's a canonical ensemble and a grand canonical ensemble, and there are others, which essentially keep various sets of parameters constant. Okay. The purpose of these ensembles, or the reason for introducing them, is that the molecules are not always independent, right? Real molecules do, in fact, interact with one another because there are intermolecular forces, so they're not all monatomic ideal gases, right? Most of the more interesting cases involve things where there are meaningful intermolecular forces, and so that idea isn't really, the idea of saying they're independent particles is not really accurate, all right? So a better way to be able to try and handle this is to use what is known as an ensemble of small collections of particles, okay? Where each molecule, we can think about these things and we get these so-called microstates. The canonical ensemble says take some set of molecules, a big enough set of molecules that you can have interactions between them, but not so big that it would be ridiculous to try and calculate those interactions, right? So if I'm thinking about a gas, for example, the intermolecular forces act only over very short distances, so I'm not going to need to have a whole lot of molecules in one slice of my system to be able to introduce some representation of the intermolecular forces. Okay, so I have an imaginary collection of these identical replicas of a system, right? Each one of my little subsystems contains n particles. They're all at the same temperature and they're in contact with one another, right? And so the total energy of the ensemble is going to be fixed because I have a fixed temperature and I have a fixed total number of molecules, right? The energies of the individual sets of molecules are not necessarily fixed, right? Because if I took a gas, if I grabbed lots of sets of 10 molecules, say, out of a gas, I wouldn't always grab 10 molecules that all had exactly the same kinetic energy. Right? So I would have some of my samples would have larger total energies than others. That can be true still in my canonical ensemble. And so this is a little bit of a visual representation of this thing. The various subsystems there, in this case, there are 20 of them drawn, just numbered 1 through 20. Right? They each have a number of particles, they each have a volume, they have a temperature, and those are all the same across all of those systems. Okay. Energy can flow across the boundaries between one of those subsystems and another. Right? That means that each individual box in there does not have to stay at fixed total energy. Energy could flow along there as long as the total energy of the entire collection stays constant. Right? Can exchange energy between the members. Okay. This construct would allow one to be able to construct a partition function. Okay, we're not going to do the hard work of trying to assemble equations for that. We're going to just write some things that are really analogous to what we did when we wrote our molecular partition functions, and so we'll just sort of go to some results for these. But this idea can be used successfully to think about particles that really do interact with one another. And that's why this notion exists. And that's because most of the, again, if you're going to say some molecules are going to react, you want some chemistry to be happening, you can't really have a reaction that takes place between non-interacting particles, right? That doesn't really even make sense to start to think about. So what we're going to do is develop some equations that would get us from partition functions to thermodynamic quantities. Right? Word of warning, this video and the next one, which I broke down into two relatively shorter ones just because they're awash in equations and some of them are a little daunting. Okay, I want us mainly to focus on what happens out of these equations and the fact that we can find a route to get to thermodynamic properties, and not too much on the details, but there will be lots of equations floating by in these this next pair of segments. Okay, so the entropy in statistical mechanics can be related to the weight of the distribution function. Okay, the W there is this statistical weight. We talked about that at the outset of this chapter, as saying that the most probable distribution of molecules across the states would be the one that had the largest statistical weight. right? So this says that the entropy S is equal to Boltzmann's constant times the natural log of that statistical weight. Right, that is a formal definition of entropy. It is somewhat notoriously inscribed on Boltzmann's tombstone, I am told, although I have not actually visited. This is different looking than other definitions of entropy that you've probably seen, right? In chemistry courses, in Gen Chem, for example, we always talk about the idea that entropy is related to this notion of disorder on the molecular scale, right? If you talk about entropy in other contexts, in physics or probably in your engineering classes, you often start off by saying the entropy is the integral of dq over t, right? And so this does really correlate with those things. In the case of the disorder, a more disorderly arrangement, there's going to be more ways to construct that, right? So its weight is going to be higher. If you think back to, gosh, and what was probably the first segment about statistical mechanics, about chapter 5, I had a slide where I had some energy levels, a set of energy levels, and I had molecules distributed across them. And I started off with a state in which all of the molecules were in the same energy level, right? And that one had a weight of just 1 because it was the most organized state, because everything had its energy level specified, right? As we got towards cases where they were more uniformly distributed across the levels, we got weights that went up to be quite large numbers, right? And so as we go up in that disorder, or the number of ways to construct the particular arrangement, the weight will increase, and this says the entropy will increase, right? Because if W goes up, then entropy goes up here as well by that equation. We know that entropy decreases with decreasing temperature, right? Because there are fewer possible arrangements at lower energies, right? We know that we want entropy to go to 0 at 0 temperature, right? That's the third law of thermodynamics, says the entropy of an ideal, pure, perfect crystal of any substance at 0 Kelvin is 0 according to the third law. That will happen with this definition, because if I get to that perfectly orderly arrangement of things, then my weight should go to 1. Right? And so if I get to where there's only one way to arrange things, then this equation also does take my entropy and bring it down to 0. So far, so good on linking that with things that we know about entropy coming in. We want to take this entropy definition and connect it up with the partition function, right? The partition function can be related to that statistical weight, and so we can work with this from there. What I've done here is I've just grabbed a couple of equations, right? And so my Q, the uppercase Q partition function, is going to go in here for in this equation here, right? My U's there are internal energies. U0 is just the internal energy of the ground, or the lowest energy state, which we've been taking as 0 throughout, and we could in fact continue to do that, right? If I want to take that equation and write it in terms of the molecular partition function, I use the result that we had before, right? Which was that I replaced my uppercase Q here. I'm replacing with this one. That gets me the result on the bottom here. Okay, that is an equation that, at least in principle, can link an entropy value to my my molecular partition function, right? And we know how to calculate that that molecular Q, and so that's something we can do a little bit of work with. If I take that last equation and I again do the Stirling's approximation to get rid of the n factorial there, right? We can do a little bit of rearranging and get ourselves to this result here, right? And you can look through the equations. Your textbook does most of the work and walks through these equations as well. And so you can check up on those to the extent that you like to do such things, right? So this gives us an expression that gets us entropy. We have also expressions for the internal energy in terms of the partition function, right? If we have those two, if we have entropy and we have internal energy, then we can start to assemble a number of other thermodynamic functions, because if you think about it in sort of traditional thermodynamics, the more these functions you get, the more readily you can relate things to them, right? And so we'll make some progress in that direction momentarily. First, a little bit of a pause, and I again decided to leave in one of these, what would be clicker questions in the actual class. It says, as temperature increases, the probability of a particle occupying a particular quantum state, meaning just pick out one quantum state at random in the available list. The probability of a particle occupying that state increases, decreases, stays the same, or the last choice says it depends. It may increase or it may decrease. So take a moment and think about that. I'm going to start by sketching out some energy states over here just to give myself something to work with. So suppose I had a set of energy states that looked like this. I don't know, I'm just making this up, obviously, but suppose they look like that and energy is increasing, going up. All right, so let's talk about what we know about what happens here as the temperature changes, right? Suppose I start off at very low temperature, right? If I start off at very low temperature, as the temperature goes to 0, all of my population, all of my probability is supposed to congregate in the bottom state. Down here, I just have 1, right? So as temperature goes to 0, I have my probability for the ground state, what I'll call P0, that has to go to 1, right? If I think about it, as I raise the temperature, I begin to grow some probability in the states going up the ladder, right? As that happens, effectively, it can't be true that they all increase, right? If they all increase or all decrease at the same time, then I'm not conserving total probability, right? The total probability has to be equal to 1. And so in order to get, if I come back later, suppose I went to infinite temperature. If T goes to infinity, it's a really ugly infinity, sorry. If T goes to infinity, then all states have equal probability. And you could prove that by looking at the equations. All states go to equal probability, right? So between those two limits, it has to be true that, that some are going down and some are going up, right? And so the correct answer to the question is down here. In other words, if all the probabilities were going to increase at the same time, that would somehow mean I was getting more particles, which I'm not, right? If I pictured having, like, I don't know, if I had a set of 5 particles that were all starting in this state, if I start raising the temperature, the only way to have one show up here is to take it away from down there. Right, and so anytime one probability goes up, probability someplace else has to go down. Right, it is true in the limit of infinite temperature, then things get spread out uniformly, because then there's infinite energy available, and so the population doesn't then discriminate based on the energy of the particular state in question. So it's a fun little question to think about. In actual classroom discussion, we usually have some good back and forth about what's going to happen there in different pockets of people. All right, so we earlier had this result for internal energy, right? The one that's written up here in terms of my molecular partition function, we used that specifically when we were talking off and on about the heat capacity as we built up the different pieces of that molecular partition function, right? And so in that case, we took the derivative of that expression to get ourselves to a heat capacity. And that's what we've actually got down below here, right? So this one, this one gave me the heat capacity equation that we've used before. And we see that also points out that we have the internal energy equation, right? In this instance, this is the equation that I'm really looking for, because what I'm going to do next is I'm going to put together the so-called Helmholtz energy, because that's one that we can get easily once we have the internal energy and the entropy. So the Helmholtz free energy, again, in general chemistry, we talk mostly about the Gibbs free energy, which is one that is particularly near and dear to many chemists. But there are other variations of free energy that have different sets of things held constant, right? The Gibbs free energy, for example, has P and V generally held constant, right? I'm sorry, P and T held constant as we do things, right? Because when we do the T delta SPs, for example, in that we take the T through the derivative. The Helmholtz free energy, the definition of that is this one. It's internal energy, right? Because U minus U0, that's just the way our textbook always writes the internal energy. It just says that's relative to some reference point, right? So U minus TS is a definition of the Helmholtz energy, right? Contrast that with the Gibbs energy, the one we use more often in chemistry, that one is enthalpy takes the place of the internal energy there, right? And so this one, the Helmholtz energy, is actually going to be useful at constant volume, where the Gibbs energy is useful at constant pressure, because that's where the delta U or delta H are the go-to energy related piece, right? So we have that equation to define the Helmholtz energy. We have equations for both the entropy and we have the internal energy piece as well, right? And so I can set up what's going on here. This is my my entropy result, right? Which, as I pointed out, it's pretty awkward looking up here, but we're going to take that and we're going to put that in. So that becomes the piece in the curly brackets down here, right? That is my entropy piece. When I do that, I see right away that I have a U minus U0 out here. Here I have U minus U0 over T, but that's inside where it's being multiplied by T. So this term and that term out there will in fact cancel one another, right? Here I've got an NK there and an NK there. And so everything in the curly brackets now contains an NK. And so what this last line has done is to pull the NK out of the brackets with the minus T out here. So I get minus NKT, and then I get just this piece inside the natural log of that Q over N from the partition function, plus there's a 1 in there, right? In terms of my my Q itself, the ensemble partition function, the equivalent result is actually this one, right? Where that now is getting me a result for the number of particles that's in my ensemble, right? Because the N is now gone from that. Okay, so that would give me an expression that lets me get this Helmholtz free energy. I will be able to go ahead and do other things with that, and as my repertoire grows and I have more and more of these functions available, the pathways to get to still more of them also open up more readily. One thing the Helmholtz function is easily related to is pressure. Okay, and so the pressure can be written this way. It's just the derivative with respect to volume of that that Helmholtz energy, where the derivative is taken at constant temperature and fixed number of particles. Right. So now we have an expression for the Helmholtz energy, and that's this one. Right. So all I have to do is take this and put that in here for A, which I've done here, right? That just says we write out this one. If you actually work through that derivative, it turns out that we should get this result, right? So my my pressure, according to this, is just given by NKT, and then I have the derivative of lnq with respect to volume. Right, so that says I would be able to get a value for pressure by taking that and using my partition function to get to a pressure. Right, so we're beginning to open up doors to get from this partition function, which again we get from quantum state information from spectroscopy essentially, and we're looking now at ways we can use that to get what are normally more thought of as more experimentally measured properties. Okay, so let's take that result there and actually apply it to a system where we kind of know how the answer should turn out. Okay, so I'm going to use that relationship that we just got for the pressure, and we're going to try to derive an expression for the pressure of a set of n non-interacting molecules. Okay. A set of n non-interacting molecules would in fact represent an ideal gas of n molecules, right? And so we know what the pressure should turn out to be because we know the ideal gas law. So we'll be able to check up on how our result compares to what we should expect, okay? So here are the things I need. I have my pressure P is equal to NKT. Then I have derivative of log of Q with respect to volume. That's at temperature and number of particles, right? And if I want to take that, I could rewrite that expression and I could write it as NKT over Q, and then my derivative becomes just derivative of Q with respect to volume. Okay, that's still at temperature and N over here for what that's worth. Okay, I know my expression for the partition function, right? I know that my Q here is going to be the translational partition function because I'm just doing an ideal gas. I don't have any other things going on, right? And so if I do that, then my expression for that says I get this 2 pi m kt over h squared. All of that is to the 3/2 power, and that's all multiplied by v, right? So the derivative that I want, that says my derivative of q with respect to v is just equal to the constants in front of that, right? 2 pi m kt over h squared. I do really know how to make a 2, I promise. And that's all to the 3/2 power still, right? So that's my derivative. And now I can take that and just bring it in up there. That's going to give me my P is equal to nkt and I have nkt over a q down there, right? So down here, I get my q again. So that's my 2 pi m kt over h squared, all to the 3/2, and now it's still times volume in there because that's just q, right? And then up here, I'm just getting this piece from here, right? So that's just the constants, 2 pi mkt over h squared, still 3/2 power. Right, so I get to kill off this piece and this piece, and I'm left with n k t over v. K is a little awkward looking there, but pretend that's a k. Okay, I'm not making it any more k-like, am I? That gives me what you may recognize as the ideal gas law. If you don't recognize it as the ideal gas law, you just need to realize that K is R, the gas constant, divided by Avogadro's number, right? So in this version, N is number of molecules, instead of in our perhaps more traditional version where we have little n RT. In that one, N is the number of moles, right? But those two things are equivalent, right? So this is the ideal gas law with the number of particles just expressed in individual molecules rather than in moles, right? So our formalism here definitely works for the trivial case of doing the ideal gas law. That means, well, it points to the idea that it should also work in other cases where we don't necessarily have the ideal gas law to work with, right? And so although we're only looking right now at a result which we in essence already knew, we still can take some comfort in the fact that we do get the expected outcome here, and that should help us to believe that we would get a correct value if we do this in other cases. All right, I decided to break this into two pieces because, again, there's just sort of a lot of these equations and derivatives flying by, and so I think it might make for easier digestion in smaller bites. And so this will wrap up part one of the tour of thermodynamic properties. Part two will come along next, and we'll work our way towards things like enthalpy and Gibbs energy in that one. Thanks.